Hi guys, my name is Franz, and in this video, I'm gonna explain the pumping lemma for regular languages. For this video, I'm assuming that you guys already know regular languages, DFAs, all of that, right? Okay, let's get started. The pumping lemma for regular languages is used to demonstrate that certain languages are not regular. This is the idea. We're gonna take a language which is not regular, assume that it's regular, apply the pumping lemma for regular languages, and get a contradiction somehow. Therefore, our assumption that the language is regular is flawed, and the language is not recognizable, you can say. Now, keep in mind that it's always the same process, always. You're gonna take a language that is not regular, assume that it's regular, apply the pumping lemma for regular languages, and get a contradiction somehow, right? Now, a language is regular if there is a DFA that represents it. If there is no way to draw a DFA for that language, then the language is not regular, and you apply the pumping lemma for regular languages to prove it. I'm not gonna go over the reasons why a language is not regular. It's not the purpose of this video. I'm just gonna explain the pumping lemma for regular languages by itself. How it works, fair enough? Okay. Now, what's the motivation behind the pumping lemma for regular languages? Well, the pumping lemma for regular languages is a consequence of the pigeonhole principle, and I'm gonna explain why. But before that, let's just say the pigeonhole principle. If you have certain amount of pigeons in some pigeonholes, and the number of pigeons is greater than the number of pigeonholes, then there will be some pigeonholes with at least 2 pigeons, right? This is an example of the pigeonhole principle. Here we have 5 pigeons and 4 pigeonholes. How do we fit all the pigeons in the pigeonholes? Well, you can go this way. This one goes here, this one here, this one here, this one here, and this guy is like, what? Where does it go now? Well, it got fit in here, right? Now, how do we apply this concept? How do we apply the pigeonhole principle to the pumping lemma for regular languages? If you have a DFA with, let's say, P states, remember P states, and you have a string W which is at least as large as P, remember, W is at least P, then you're gonna visit the same state at least twice. Let's see an example. Here we have a 2-state DFA. Of course, we don't really care what the language is. It doesn't really matter, right? Now we set P as the number of states, which is 2 in this case. Now we have a string W, which is 1, 0, and the cardinality. The length of W is 2, because it has 2 characters, 1 and 0. Now, pay attention to this. The pumping lemma for regular languages only applies if we have a string which is long enough. How long? Well, at least as large as P. That way, we're gonna visit the same state at least twice. In this example, the length of W, which is 2, is at least P, which is also 2. Now, for the string 1, 0, you go from Q0 to Q1 on getting input 1, and you hit Q1 for the first time. Then you stay in Q1 on getting input 0, and that's when we visit the same state at least twice. In this case, Q1. We're hitting Q1 for the second time. Now, how do we apply this concept? How do we compare this idea with the pigeonhole principle? Well, the pigeonhole principle only happens if there are more pigeons than pigeonholes. The pumping lemma for regular languages only applies if the length of W is at least at least P. In the pigeonhole principle, you have some pigeonholes with at least 2 pigeons. Here you hit the same state at least twice. In this example, we hit Q1 twice on getting input 0, right? Okay, let's see a more general example. Let's say we have this 5-state DFA, and the value of P is 5, which is the number of states. And there is a string W of length 5, and the DFA accepts W, where the length of W is at least P, right? Now, in general, when we solve problems in the pumping lemma for regular languages, we're going to choose a string, let's say W, and divide it in 3 parts, X, Y, and Z, and the language accepts W, or in this case, the DFA accepts W. It has to accept W, always, where the length of W is at least P. Otherwise, we couldn't apply the pumping lemma for regular languages, right? So we write W in terms of XYZ, and the DFA accepts W. Now, the red part in the DFA is the white part in the string. That's what we call the looping part. Okay, now the pumping lemma for regular languages is called pumping because you're gonna pump up or pump down only the variable y. And what does that mean? It means that if the string xyz is in the language, then the string xyyz is also in the language when you pump up. If you pump down, then y becomes empty, and will generate this string xz, which has to be also in the language. Now, in this example, we choose 001 as the y part, because that's when we visit the same state at least twice. In this case, Q0. You can see here that we visit Q0 for the first time on getting input 1. Then we process 0. We process 0. And then we process 1. And we hit Q0 for the second time. Right? Now, when you choose a string in the pumping lemma for regular languages, the y part is never empty. Never. Because there must be something you can pump up or pump down. X and Z can be empty. Not in this example, of course. I mean, in different examples, they could be empty. Because you only pump up or pump down the y part, not the X and Z part. Fair enough? Now, as I said at the beginning of this video, we always follow the same steps, the same process. You take a language, L, which is not regular. Then you suppose that L is regular. Remember, we're going to assume that L is regular. Now, if L is regular, then there is a variable P, which in practice is the number of states, right? And P is called the pumping length. Then there is a string W, which is at least as large as P. Now, the string W can be written in terms of XYZ, right? And once you have W equals to XYZ, there are 3 conditions that all the regular languages have, and we use them to prove that a language is regular. The first condition we already saw, y is never empty, so we can pump up or pump down. The length of sy is at most P, and I'll show you why this condition is always true by using an example later, okay? And the third condition is the one that has to do with the pumping lemma concept. That is, SYIZ is in the language, is in L, for all the values of y greater or equal to 0. In other words, if SYZ is in the language, then SYYZ is also in the language when you pump up. If you pump down, XZ is in the language. And that's when I is equal to 0, right? Okay, and finally, once you apply the third condition, which I call the pumping condition, you get a contradiction, always. You always get a contradiction when you apply the third condition. And you conclude that L is not regular by contradiction. And that's the last step. Okay, let's look at the first example of this video to summarize everything we've seen so far. The length of P is 2, which is the number of states. Now let's choose a string which is long enough. It has length 4 in this case. So this is the string 1, 0, 1, 1. And the length of W is at least P. So the pumping lemma for regular languages applies, right? In this case, the Y part consists of a single 0. The first condition, Y is never empty, you know that. Otherwise, you wouldn't be able to pump up or pump down. In general, X and Z can be empty. Even in this example, you can see that the Z part can be empty. Because if we remove Z, we're still in the language. It will be like 1, 0, 1, and 0, and you wind up in Q1, which is the accepted state. So you're still in the language. Okay? We don't need Z, but we do need X to get Q1, the accept state, right? It could be empty in a different example, but not in this one. Now, the length of Sy is at most P, and I'm going to explain why later. Okay, the third condition, which I call the pumping condition, Syi is in L for all the values of I greater or equal to 0. Now let's look at the transition function. The looping part is in red, as before. That's the Y part that we're going to pump up or pump down. So you start in Q0 and you go to Q1 on getting input 1, right? Like this. Then you stay in Q1 on getting input 0. And that's the Y part, because we hit Q1 twice. We hit Q1 for the second time on getting input 0. Then we have the Z part that we don't really care because it could be empty in this example, right? Now, you may say, hey Franz, I can get a bunch of zeros here in the Y part and still be in the language and break this condition, the second condition. You get a bunch of zeros here in the Y part and you make the length of xy greater than P and you break this condition. Well, that's true, but that's because in this particular example we always hit the same state, which is Q1 in this case. The Y part always hits Q1, always, and Q1 happens to be the accept state. So no matter how many times we hit Q1, because Q1 is the accept state, right? So when we bump up, we're still in the language, right? And you can even start with this string. Let me show you. Now, the length of W is 5, and we have this string, and this will be the transition function, having the Y part that hits Q1 twice, right, with the two zeros. Now we pump up, and we get this string, and we're still in the language, of course. And just for the record, we can also pump down and get the same result, okay? Now, pay attention to this. In this particular example, what will happen if the Y part involves more than one state? Because now, the Y part only involves Q1, right? We're just hitting Q1 here twice in the Y part. But now, what will happen if the y part involves q0 and q1? Well, to see what happens, let's go back to the previous string that has length 4. Now, let's get rid of the x bar, like this. Now we made the y part consists of 1 and 0, right? And also, the y part now involves q0 and q1, right? Because this is the y part now. Now, what happens when you pump up or pump down? Let's just pump up, okay? We have this string and we are out of the language because this string is not longer in the language. It will be like 1, 0, 1, 0, 1, 1. And you wind up in q0, which is not an accept state. So you're out of the language. And that's another reason why we need the x part in this example. Fair enough? Okay, let's break this condition again in a different way. Okay, we're gonna make the length of xy greater than p, like this. In this case, the length of xy is 3, 1, 0, 1, right? The length of xy is 3, which is greater than p, that is 2. Okay, so we break this condition. Now, what happens when we pump up? We get this string and we're out of the language again because it's gonna be like 1, 0, 1, 0, 1, 1, and you wind up in q0 again. So you're out of the language, right? Okay, to conclude, when you break this condition, the second condition, and you pump up or pump down, sometimes you are in the language and sometimes you are not longer in the language, as you can see. And also, the x and z part can be empty sometimes, but not always. In this example, the x part is not empty. Otherwise, when you pump up or pump down, you're out of the language, as you saw, right? In the previous example, the x and z part are not empty. Otherwise, you couldn't get the accept state, right? If you want to practice and have fun, go and change the y part and try to make the x and z part empty. For example, you can make the x part empty by making the y part bigger, right? Just like we did before. And you'll see that when you pump up or pump down, you'll be out of the language, just like the other example. So the x part and the z part can be empty, but not always, okay? Now, going back to the condition, the second condition. As I said, when you break this condition and you pump up or pump down, sometimes you are in the language and sometimes you are not. And that's why this condition is always true, because by having this condition satisfied, I'm making sure, I guarantee, that when you pump up or pump down, you will always be in the language, always. And no matter how many times you pump up or pump down, you will be in the language, always. Fair enough? It's the same story when you have more than one accept state. So, don't you think that this is exclusive for the DFAs with one accept state? Trust me on that. Or you can go and have fun with the DFAs that have more than one accept state. You know, you take a string, you choose the y part, and so on. And you will get the same result. Okay, that was the complete explanation about how the pumping lemma for regular languages works. I hope this was clear, and in the next video I'll show you the first real problem of the pumping lemma for regular languages. So, thanks for watching and see you next time.